SwayamPrabha. Digital India. Educated India.
Okay, so yeah, we're going to discuss about POD analysis that we had done. I'm afraid you'll have to go through with me the small letters here. What we are trying to do is use POD as a tool to investigate instabilities. That's a new direction that we have given to the subject over the last couple of years. And I discussed about specifically flow instability for flow past a cylinder, right. It is a blob body flow that we have studied. Now, we are trying to ratchet up the difficulty to one level more. Today, we are going to talk about another flow. It is an internal flow. So, we have discussed about an external flow. Today, we are going to talk about an internal flow and then show that the modes that we talked about 3 classes of modes, if you recall. We talked about the regular modes, then we of course talked about those anomalous modes, and there we talked about the first kind and the second kind for flow past a cylinder. So, now we are going to see are these generic enough to be visible in other flows also. So, what we have done, we have undertaken to study the same thing for an internal flow. This is basically a lid driven cavity problem. So, a lid driven cavity problem is as it is shown here. What we are going to show you here a picture that will demonstrate what is going to happen here. We go through the same process of solving the Navier-Stokes equation and get those solutions, then obtain the instantaneous flow, then you obtain the mean flow, and then what we are going to do is basically calculate the disturbance flow, and once you have the disturbance flow, you obtain those Galerkin projection that we are seeing, and this is what your driven cavity program is. What you have here is basically a square cavity here. The flow is set up by moving the top lid from left to right at a constant speed u, and then we focus our attention on 3 representative points marked here as P. P is a topmost right corner point, and Q is this bottommost right point, and R is over here. Now, what you notice is depending on where you focus your attention, you see a different time evolution of this disturbance vorticity as a function of time. However, the common feature that you are seeing here is almost the same, that you start off with a semi-quiescent stage, which is perturbed by linear instability, and that linear instability is modulated by nonlinearity. That is the typical picture that we saw. What is the essential difference between this flow and the flow past a cylinder? Here the initial flow is very chaotic, whereas in case of a flow past a cylinder, what we saw, flow was completely steady. So, we saw the instability was building up on a steady flow, and here what you are seeing, the linear instability is building up on a very transitory flow. I mean, it's showing very massive transients, right. Now, if you of course look at the other point Q, Q is what? Q is one of those corner vortices, that's Moffat vortices that we call. And even there, what we are seeing is the disturbance growing with time, but at the same time the mean is shifting. Recall we talked about the shift mode. What was the shift mode? Shift mode was this. This was what we called as the shift mode. So, here also we are seeing the same kind of thing, that the mean is shifted, but overriding that mean you have the fluctuation that grows linearly and non-linearly saturates. And this is this point which is outside this corner vortices, which also displays the same thing. So, in a sense that what we are talking about here is the same type of behavior that we saw, but now let me show you what we are going to see. If we now obtain the equilibrium amplitude and plot it as a function of Reynolds number, then what we are going to get is the equilibrium amplitude versus RE for this lid driven cavity problem. And exactly like what we saw there, it is not a purely parabolic profile as Landau equation would have demanded, but instead you are going to get this equilibrium amplitude to fall on various polynomials, and then that in concert with what we have talked about earlier, we talk about multiple Hopf bifurcation, and different Reynolds numbers are noted here. As you can see, the first one is around 7,933, the second one is at 8187, and the third one that we have shown here is 9933. So, essentially whatever we have seen for flow past a cylinder, that is depicted here, and the corresponding experimental results by Strijkowski is shown here, you do get to see as exactly a similar phenomena, that it is not purely given by the Landau equation, it falls on various branches of bifurcation, and this of course lends credibility to what we have been talking about this in terms of universality of this kind of instability modes. And this was the result that I told you about Strijkowski's experiment, and you can very clearly see there is one set of data here, another set of data here. So, this is not something that is construct of the computations, it does come out from experimental viewpoint also. Now, if you look at the eigenmodes for this driven cavity problem, you can go through that. Remember, we have shown the disturbance vorticity in the Galerkin setup, a time dependent amplitude am of t times phi m of x. So, space time dependence has been split up, and if you perform that POD analysis, this eigenfunctions are plotted here. So, these are your eigenfunctions. This is the first mode, this is the second mode. They appear pairwise, as you can see. The solid line and dotted line will toggle you between the positive and negative vorticity, and you can see that same structure that we talk about. There is a core, and there is the main satellite, and there are the secondary ones. This is what we see. And what is this? This is nothing but your anomalous mode of the first kind, the shift mode that we talked about, which appears singly. This has got no pair formation. Then of course, that would mean that if I am calling it 3, 4 would be the missing one. So, this we have 5th and 6th, right. Again we have a 7th isolated one. This is also shift mode or anomalous mode of the first kind, or T1 modes that we talked about. Now, these are two pairs, these two are pairs, but they belong to this T2 kind. And how do we know? Well, you have to plot the amplitude functions. You will have to plot am of t And once you do that, well, here are the pictures. A1 and A2, as you can see, is plotted here. They do indeed follow like Landau equation. That is why we call it a regular mode. This is your mean 0 line, and you are seeing the fluctuations, right? And we have the third mode here, which was that shift mode we talked about, which appears singly, and that you can see is that it does not start off from 0 like flow past a cylinder, because of the strong transient nature of the flow to begin with. So, it starts off with some value, but it does go and settle down eventually there. And this is another regular mode pair. You can see that during the transient state, they do not have the pure orthogonality kind of that you expect from POD modes. POD modes are supposed to be orthogonal, but they do not remain so. So, it's very instructive for one to understand what is going on here. Our aim is to take a very stochastic system and project it on a deterministic basis. And if we do that, then what would happen? If we are getting a perfectly deterministic basis, those have to be orthogonal. 1 and 2 seem to show that. But if you look at 5 and 6, to begin with, they are not orthogonally related, right. Despite that, as instability takes over and nonlinearity saturates, you do actually end up getting a orthogonal basis, right. So, in contrast, we have this shift mode of the anomalous mode of the first kind, the third and the seventh. That is what we are seeing here. And I told you about the 9th and 10th, and there it is. So, 9th and 10th and 11th and 12th modes, they look like this. And this is exactly what we say, like this mode amplitude will grow as you would see in a wave packet, and this is what we are saying here. So, that is the way to go about. You do the singular value decomposition of the correlation matrix, you get the eigenvalues, that also gives you an idea of pair formation, etc. Then you look at the eigenfunctions, that gives you some additional information about it. But whether they are truly going to give you this sort of classification into regular and anomalous modes or not will be very clearly brought out when you take a look at that amplitude function A m of t. So, this is a 3-step procedure. You cannot just simply look at one set and comment about it. One thing you must realize also, though, that people in performing POD have not been cautious enough. You are doing direct simulation here. You may be doing the same thing in an experimental framework, right. But then when you are trying to do POD, what is its sampling rate going to be? That is a very vital question. And that is where I think the rest of the world has really not done the homework properly. Because if I am doing a kind of a sampling of a time dependent function, then I have to do it properly to capture the appropriate frequencies. Most of the time people do is they may be doing high fidelity calculations, but when it comes to POD modes, they have been niggardly. They take far fewer frames. And then of course, the moment you decide upon the sampling rate of POD analysis, that restricts you to what you are seeing. And tell you what, this kind of simulations have been done to pick up this kind of frequencies. If I would have taken here what you are seeing here, we have shown it from 200 to I think 600, that is what we are showing. So, here the time interval is about sampling rate is of the order of about 0.01, 0.02, that kind of a thing. So, you can imagine the volume of data that you will have to handle to do a POD. And if you do not do it, of course, you will not pick up all these frequencies. So, you must pay heed to the requirement of resolution, and this is a very, very vital issue that we must talk about. Now, these are some of the things that we have seen for our circular cylinder. So, there is no question about it, and these were also the sort of mode shape that we have seen for flow past a cylinder. We have seen that the regular modes here 1 and 2, then we have the shift mode, then we have another set of regular mode. This is a very interesting thing what you are noticing here, that in the end you get to a regular mode, but in the transient phase once again they are dissimilar. The individual components, they are dissimilar. Same thing over here. Should we call it a kind of a T2 mode, or it is a kind of admixture of a T and R mode? Whatever we do, we need to understand that these elements are the basic ingredients. Whatever we are seeing at the end of the day is basically a kind of a mixture of all these things that we see. Now, this is what you are going to get when you look at the DNS of that internal flow, and here also you can notice that despite the talk of universality, there is some bit of difference in behavior of the successive modes at different locations, but by and large you can really capture the events that we are noticing. Essentially, that linear instability followed by nonlinear saturation and mode behaviors belonging to either of these 3 generic classes. Okay, so I suppose one can go ahead and do all this. These are those mode shapes for cylinders. Anyway, I think what we are essentially looking at, this is a mode shape for flow past a cylinder at Reynolds number of 60, and again you can see these two are those regular modes. This is the T1 mode and this is a T2 mode, and so on and so forth. So, you can study these as a sort of a universal building blocks. Okay. So, I think what I would do is I will close the discussion here on POD analysis. I suppose you have now seen quite a bit of variations. Now, we go to the last phase of our course, and that is basically talking about turbulence. So, if you look back, that flow that we see in nature or in engineering devices, most of the time they are going to be turbulent, despite the fact that this part is considered to be a special topic in studies of fluid mechanics, but it is a sort of a interesting thing, because this is not the exception, this is the rule. All flows are turbulent, but very little attention is paid to it. There are various reasons for it, because we still do not understand what turbulence is. That is what we have said, that there are no precise definitions of turbulence. There are lots of people who can rattle strings of sentences, turbulence is this, turbulence is that, etc. They essentially tell you about the characteristics of most of the turbulent flows. I am going to talk about some of those characteristics one by one, but please do not misquote me by saying turbulence is irregular flows, just one of it. It is not going to be adequate. The flow behavior, if you look at it, whether you are looking in space or in time, you would see that there would be a sort of apparent dichotomy in showing that there is a lack of coherence. What you see is basically some kind of randomness, or it is, if I look at its time variation, it is going to look like chaotic. Okay. I purposely wrote this word chaotic in the sense that chaos dynamics was a topic of intense studies in starting from 70s up to probably even now. Today lots of people try to study a lot of aspects of chaos dynamics, although it started off in some of the work done by fluid dynamicists in trying to explain turbulence. It has not fulfilled its promise in defining turbulence, because what has happened is, irrespective of this randomness and chaos that we try to characterize turbulent flow with, people also know turbulent flow in its underlying features have some kind of deterministic structure. And you are now really ready to appreciate that point of view, because that is what we have done with our POD analysis, that we will take a completely stochastic dynamical system and project it onto a deterministic basis. So, those deterministic bases are nothing but your so called coherent structures of turbulence. Okay. That is why people may like to study turbulence using statistical method, or they may like to study in a dynamical system framework like what we have just now done. Now, so irregularity is one of the feature of turbulent flow. There is this other feature, is diffusivity. If you go back when we were discussing about bypass transition caused by those convecting vortex in the free stream, what did we see in this flow visualization picture? The dye that was coming out nice and straight got diffused. There was a significant increase in mixing, diffusion. So, whenever you see turbulence, you must also understand there is a enhanced mixing process that is characterized mathematically by the process of diffusion. So, diffusivity is very, very important in turbulence. They represent rapid mixing in terms of all quantities of interest. There could be mass diffusion. If I add in a sort of a dye and it gets mixed with the adjoining fluid, it is basically mass diffusion, right. At the same time, when I see a flow a shear layer developing, then flow is undergoing transition and it is becoming turbulent, and what do I see? Thickening of the boundary layer. So, what is happening? The mixing is occurring over a larger wall normal distance. That is what we are talking about, enhanced mixing of momentum. And of course, when mass and momentums are transferred, you of course have to understand that would lead to energy transfer too. Okay. What you need to understand, that if you did not have the turbulence, then the boundary layer, the shear layer would have grown, and that mechanism was given by kinematic viscosity, the molecular viscosity. So, molecular viscosity is like one layer of fluid going over the other, and then they are transferring momentum in orderly fashion from one to the other in a macroscopic sense. But in a microscopic sense, you can think of in terms of those molecules or the constituent particles exhibiting rapid variation, but in a macroscopic sense they are still very regular. However, when you have turbulent flow, even at the macroscopic level, you are going to see a massive increase in diffusivity. So, if I try to characterize my turbulent flow in terms of a diffusivity coefficient, that coefficient of diffusion has to be significantly higher than what you get in laminar flows. So, that is what we are saying, that this is one attribute which is very stronger than your molecular diffusivity. This is something very, very important. And unfortunately, this point of view also is the motivation to describe turbulence in terms of a diffusivity coefficient. That is what is goes by the name of eddy diffusivity, or that is modeled most of the time in turbulence models. But please do not try to understand, like in the name of engineering fluid mechanics, a lot of people understand turbulence in terms of coefficients of turbulence models. That is far from the truth. This is one of the attributes of turbulence, that you do have enhanced diffusivity. That eddy diffusivity is associated with the eddies. What you are going to see in a turbulent flow, you are going to see in a turbulent flow is the multiple presence of eddies of different sizes. So, you have a hierarchy of sizes of eddies. So, that is why this is what is called as the eddy diffusivity. So, in a sense what we are talking about basically is that different size eddies interact with each other, and we have seen from the Navier-Stokes equation that the nonlinear term in the convection path helps you do that through the process of cascading, right. We talked about it. We'll talk about it in greater detail as we go along. There is the other thing that is very typical of turbulent flows. You would hardly ever get turbulent flows which is occurring at low Reynolds number. But please do mark my word very, very, very carefully and cautiously that whenever we are talking about turbulent flows, we are talking about turbulence that is generated by some mechanism and which is also self-sustaining. Remember that experiment that we seen when we dragged a single vortex? What happened when we removed the vortex? Things again came back to normal. Would I call that a generic turbulence? No, because that was more like your forced vibration. But when we are talking about turbulence, we are more like talking about natural vibration, right. So, it is self-sustaining, it should be there, it should be there, and that kind of self-sustenance comes about when your basic equilibrium flow is unstable. So, instability is the core of everything. See, that is why in this course, although it is titled Transition and Turbulence, I have spent most of my time talking about the transition aspect with the twin object. One is, of course, all these phenomena are instability driven, and number two is to basically fight the ghost of the commonly held perception that turbulence is universal. So, it does not matter how you get there, it will all be given by a single model, which is not true. We firmly believe, some of us firmly believe that there are multiplicity in the point of view of the turbulent flow itself, and what end product you get depends on which route you have traversed. And which are the routes? These are the routes of instabilities. So, what happens is the instabilities will be characterized only when you have large Reynolds number, all right. We have seen that if we have low Reynolds number flow, we can excite the flow, but it may not sustain itself. Once I remove the source of disturbance, it quietens down. But if I go to higher Reynolds number flows which are unstable, then once I get it started, it will be there, or I do not have to get it started. The small background disturbances are good enough to trigger it, right. So, this is something that we understand, that large Reynolds number is a necessary condition, not a sufficient one to tell you that all large Reynolds number flow will have to be turbulent flow, but the propensity of setting up turbulence is very much there when the Reynolds numbers are high. There is the other aspect of turbulence that we must keep in mind. This has to do with the way we look at Navier-Stokes equation. If I write down the Navier-Stokes equation, then we can understand the basic processes, right? The basic processes are very clearly understood. This is the local acceleration at any point. If I look at what the time rate of change of events are occurring, that is what is given. This is your convective acceleration. Okay? This is the way, let us say, the pressure is driving the flow. You may have it, you may not have it. Then of course, this is the viscous diffusion. Of all the terms that you see, this plays quite an interesting role. This is your nonlinear term. Well, if you are a mathematician, you would say it is a quasi-linear term, because the highest derivative is second, and that is where it is linear. But this is a nonlinear term that plays a significant role in determining the dynamics. We have already seen that all instabilities do start up from here. Why? If you recall, we have written down the Navier-Stokes equation in rotational form. What happens? I can write it down in terms of v cross omega and gradient of v square by 2. Okay? So, we could do that. What I do is, if the flow is irrotational, that term will go away. So, what the nonlinear term is doing? Just simply redefining the pressure, that P by rho plus half v square. That is what you see, what we are talking about, the role of rotationality. So, if I do not have rotationality, nonlinearity does not do much, it just simply redefines the pressure. Okay? So, this is something that we need to understand, that rotationality is central in understanding turbulence. And what about the three dimensionality? Three dimensionality is written down when you take a curl of this and then you get the vorticity transport equation, right. So, you take a curl and then you get the vorticity transport equation. How does it look like? Well, okay. So, this is your vorticity transport equation. So, what we need to do is basically look at this and understand what each of this term is doing. This term is rather important. This is what is called as vortex stretching term. Okay. You can very clearly see that this term will be identically equal to 0 for two dimensional flow. Why? Because your flow gradient will be in, let us say, xy plane, omega is in the normal direction, so z direction, so omega dot del is 0 identically. So this is what we need to understand, that this vortex stretching is only for 3D flows. For 2D flows, it's identically equal to 0. Okay. So what happens is, then you can understand that vortex stretching will only be there for 3D flows and not for 2D flows. And this is what has perplexed fluid dynamics community for last half a century. So what really happens is, this tells us when this is going to be important. So you are seeing that vortex stretching will not be there for two-dimensional flows. What does vortex stretching do actually in a real flow? That you will understand when you look at the energy spectrum. And if I plot the energy spectrum of a typical flow, inhomogeneous flow, it would be like this. This way that the energy is being transferred from small k to large k, one of the mechanisms that can do is vortex stretching. Okay? So this, when you see the slope as k to the power minus 5/3, this was what was shown by Kolmogorov, that that can only happen corresponding to vortex stretching. So that's what we are talking about, that if we look at turbulent flows, they are always characterized by three-dimensional vortical fluctuations. Vorticity dynamics, of course, plays a central role in all fluid mechanics, more so for turbulent flows, because what we have said, we have defined the turbulence as an ensemble of eddies of different kind. So eddies means vorticity, right? Circulation. So of course, vorticity dynamics has to play a central role. And then what's happening, that this process, this nonlinear process of vortex stretching transfers the energy from small k to large k. That means what? It is basically siphoning off the energy from larger to smaller eddies. That's what we are saying, that if I don't have this vortex stretching, I would not have a powerful mechanism by which the energy will be transported from larger to smaller eddies. But please do understand, a very large part of the sky is dominated by 2D turbulence. Nothing exemplifies better than the atmospheric dynamics. I will show you some results as we go along. When we look at atmospheric data, we will see that this energy spectrum is not given by k to the power minus 5/3, but it is given by k to the power minus 3. And this is an attribute of 2D turbulence. Although people used to think 2D turbulence is sort of anachronism, it was just studied for the sake of study, but lots of the people are waking up to the reality that you can have 2D turbulent flows. And Krishnan did lots of pioneering work in this. One of the postdoctoral student of Einstein working on turbulence was Bob Krishnan. He had done a lot of work. The 2D turbulence is characterized by k to the power minus 3. It is also characterized by a physical process where smaller eddies goes and merges together and forms bigger one. This is what is called as inverse cascading. So, this process that we are seeing here is what is called as cascading of energy. But 2D turbulence display what is called as inverse cascade. See, conceptually, this picture is not difficult to visualize, because what we are talking about, we have smaller eddies joining up together. It happens all the time. It's nothing very sacrosanct, but mathematically it was shown that when you have 2D turbulence, one of the attribute of that is, of course, this. That is why I specifically say that we are open to ideas of 2D turbulence as evidenced plentifully in atmospheric dynamics. We will show that. Vorticity intensification and three dimensionalization is possible via vortex stretching. That is what we talked about, a mechanism that is possible only for 3D flows. But you have already noted certain things where different scales can come about. For example, think of Kelvin-Helmholtz instability. What you have had, I have a uniform flow on top and uniform flow at the bottom. There is an interface. This interface is disturbed by some background disturbances, and this interface curls up into vortices. So, that is basically a direct mechanism of creating vortices of various sizes, right? And what we noticed, it was possible more so for a 2-dimensional flow than 3-dimensional flow. We established it. 2D flows are more prone to Kelvin-Helmholtz instability than 3D flows, remember. So, sometimes this 3D card is overplayed, but we need to understand there are many instances. This is one of such things. And what was so important about Kelvin-Helmholtz instability is that it was an inviscid mechanism. So, you do not need to have the presence of elaborate viscous mechanism to show up the instability. You can directly get it from a 2-dimensional flow. You have the shear. So, shear is of course synonymous with viscous phenomena, right. But we are talking about the disturbance growth mechanism. That could be completely inviscid mechanism. That is one thing we must understand. We already talked about inverse cascade. So, we do see that, and we have already said that spectral distribution of 2D turbulence is qualitatively different than what you get in 3D flows. And one of the central theme of this course, as we have talked about, is the phenomena of dispersion. We have seen dispersion is a very strong mechanism by which different scales can be created. Remember, we talked about those train of vortices going over a shear layer. So, I may be defining a length scale which is given by the spacing of the successive vortices. However, because of the dispersion relation, I could create a whole host of length scale. So, do not be too much be taken up by thinking only about vortex stretching and nonlinearity. Those instabilities are, we talked about linear instabilities, right. So, the linear mechanism itself can give you a whole host of length scales. So, we must be aware of this. Now, this is a phenomenological observation. The turbulent flows are more dissipative. You ask an airline operator, they will complain till their face turn blue that they spend all the money because flow is turbulent. They would love to have laminar flow. That is because we have very high dissipation in turbulent flows. Okay? We have very high dissipation, and that is not very unusual for us to understand. We already have talked about diffusivity. If I have larger diffusivity, I will have larger dissipation. So, that is okay. Physically, trying to understand what happens, if I have a laminar flow, I will have a thinner shear layer. So, this transition from a no slip wall to the fully developed flow is occurring over a thinner section. However, if I now set in motion turbulence, what will happen? This will become thicker. So, what happens is, how do I do it? I just create a very stronger motion in a macroscopic scale, which is random. That is what we talked about. Turbulence is randomness in a macroscopic scale. You have randomness at the microscopic scale even for laminar flow, but turbulence is special that it brings in the randomness at the macroscopic level. That is what is something that we need to understand. So, when I have that, what will happen? The moment I remove orderliness, I bring in randomness, then from your thermodynamics knowledge you will say, of course, internal energy is increasing. So, earlier flow was spending all its energy going along the streamwise direction. Now, you have created motions in all possible directions. So, you have actually lost a lot of ordered kinetic energy and got it into internal energy, right. This disorganized energy increase actually implies large irreversibilities. That is where your entropy increases, right. We have talked about this. So, such transformation, needless to say, will imply dissipation. So, in your fluid flow, orderliness is laminar motion, carrying motion which is coherently directed, but the moment you bring in turbulence, you have a additional source of entropy production, loss of orderliness, that leads to larger dissipation. Having said all of this, we have already emphasized this, turbulence occurs at macroscopic scale. Do not ever be deceived by thinking that it is a molecular phenomena. It is not. So, what happens is you still view the flow as a continuum. You do not have to approach the study of turbulence by looking at microscopic level. So, you look at it as a macroscopic level, the flow is a continuum, and this if I look at the energy spectrum, it just goes somewhere there, it just stops. So, it has a finite cutoff wave number. So, if I call that as k cutoff, this k cutoff corresponds to a length scale. That length scale is many times larger than the mean free path in gas flows or the molecular scales in liquid flows. So, they are not something manifestation of your flow phenomena at the molecular level. It is basically happening at the macroscopic level. So, let us try to understand the dynamics of turbulence, and this is what we would be talking about in greater detail in the next class. Today, I will just simply say that now, whatever the attributes that we have talked about, what we are saying now, let us say the velocity field, if I write it as u, it is going to be a function of space and time. You cannot have a steady turbulent flow. So, please do get away from the habit of calculating turbulent flows by time averaged equation and think that the flow is steady. Okay? So, that is something we must understand, that u will be a function of x and t. Governing equation, of course, will be given by the, if I am talking about incompressible flow, will be given by momentum conservation and mass conservation. We will start from here in the next class. F that you are seeing here, we have purposely kept a body force which could itself be time independent, or there could be other sources of bringing in time dependence from this equation, right. We have seen instability is one such mechanism, right. We saw that a unidirectional flow coming and then it is becoming time dependent, but a body force will keep it as it is for the whole domain, and the unsteadiness can come from the boundary conditions also. Okay. So, if the domain is omega, the boundary is del of omega. Okay. We will stop here.